Hello, 1324 students. As you start to read into chapter 7, you might be wondering why one would do all those things. So generally I have a lecture where I give this motivating example, and that seems to work pretty well. Plus it ties in a bunch of tools that you're going to be using. So for example, so linear programming covers a bunch of things in chapter 7, but this example I use to motivate the whole chapter. So, all right, so suppose you are organizing a rescue effort to an area recently devastated by a hurricane or some disaster, and you are tasked with loading a large cargo plane with enough water, medical supplies, and food to sustain the population at least for the first 3 days until another such cargo ship can get in there, cargo plane in there. How much of each supply should you load to save the maximum number of lives? Okay, so we're assuming that only just now we're able to get a plane in. People have been without water, without medical supplies, without food for a while. Okay, so our first go through on this in this class, let's assume that there are enough dry goods of food available, but there's no fresh water, right? And no medical supplies, big need. So if we just focus on those two supplies in this first go round, and the next time that we talk about this example, we'll add in more possible sources of relief, okay? All right, so when you think about loading a plane with a bunch of supplies, one of the things you have to worry about is the constraints of volume. How much can the cargo area of the airplane hold, and what total weight can it carry? So you have to look at the weight and volume of things. So suppose a flat of water bottles that can sustain 4 people for 3 days weighs 20 pounds and it takes up 6 cubic feet. I'm just making up some numbers there. Who knows if that's exactly correct or not. While a medical kit, and by this I mean, something with many supplies that can help at least a dozen people, takes up 8 cubic feet, and there's a box. It's all boxed in this box that weighs 10 pounds. Supposing that, and that the plane can take up to 30,000 cubic feet, that's the volume of the interior, and it can get off the ground if there is less than 40,000 pounds loaded in there. How many flats of water and how many medical kits should be loaded on the plane? Okay, so a couple of important things in here. One, we are trying to save a maximum number of lives given some constraints, and we're focusing first of all on just 2 quantities, X and Y. X is the number of flats of water, and Y the number of medical kits. Okay, so making this more mathematically, or framing it more mathematically, which is what you do in linear programming. Why linear? Well, because all these expressions here, number of lives we're trying to save. Let me see if I can save your seeing ability to see this by getting rid of that glare. I think I did it. Let's see. So yeah, so your objective, you have to figure out what the objective is for each problem. The objective here is to maximize the number of lives saved, at least for those 3 days. So we're going to maximize a function, which is a linear function of both x and y. There's no x times y, there's no x squared, y squared, or higher powers, no logs, just a linear function in x and y. Okay, so we're going to maximize that. Now, this 4 comes from the fact that a flat of, so for each flat of bottles of water, each one of those will save 4 people for the 3 days. So this term right here represents all the lives saved by the water. The 12y here, y is the number of medical kits. That 12 is there because for each medical kit, we stated over here, it can save 12 people. Supplies, enough supplies in there and so forth to save 12. Right? So we need to maximize this function, f of xy, its value, given these constraints. We have a constraint that's the weight of things in that plane. Okay, so this quantity here, 20x, represents the fact that for every one flat of water weighs 20 pounds. So if you had 10 of them, that would be 200 pounds and so forth. So this term right here represents the total amount of weight contributed by the water in the cargo. 10y, well, you should go through the rest of these terms and explain to yourself each one why it's there. The reason you have to do that, be able to know exactly why they chose which terms they chose, is because later you'll just be given a word problem and you're the one who has to decide what the objective function, this thing up here is called the objective function. You're going to have to write that yourself, as well as these constraints as linear inequalities. This maximize or minimize, that's called the objective. Mathematically, that's the objective, and the objective tells you what you're going to do to the objective function. Okay? So to be able to write these things, you have to go through a couple examples and know how to read them, right? So the 10y here must represent what? If y is the number of flats of water, kits, medical kits, 10y is there because each one medical kit weighs 10 pounds. So that's the total amount of weight contributed by the medical kits. So weight contributed by all the water, weight contributed by all the medical kits, gives you total cargo that has to be less than or equal to 40,000. Okay? Or it said over here less than, so we could actually make this into a dashed line, but this will be fine for now. Okay, so the constraints, this is the second constraint, I'm referring to what happens with the volume. The maximum volume in the cargo area is 30,000 cubic feet. We have a 6x here. That represents, you turn off the video and you finish all this for yourself, okay? Amount of volume taken up by water, amount of volume taken up by medical kits, given those dimensions. All right, so in section 7.3, you have examples like this with two variables and two inequalities. Oh, actually, sorry, there's an unwritten set of inequalities that's in here. That x and y, we have to assume x and y are greater than or equal to 0 in this application. Why? What is x? X is a number of flats of water. You can't have a negative number of flats of water. So x, just like y, the number of medical kits, those numbers have to be greater than or equal to 0. Okay, so if you graph these three inequalities, you get x and y both being greater than or equal to 0 force you to look in the first quadrant, first of all. 20x plus 10y is less than or equal to 40,000. That is an inequality, linear inequality. You went over graphing those in section 7.1, 7.2, I believe. Or we're going to get practice with those. Those are half planes. Why? Because each of them has an associated boundary line, right? So the first one, 20x plus 10y less than or equal to 40,000, is bounded by the line in the plane, 20x plus 10y equal to 40,000. Often with these problems, can you guys see over here? You can see that? Okay, good. Often with these problems, at least the easier ones, you quite quickly find 2 points on that line by simply doing this trick. If you set x equal to 0, 20 times 0, that's going to be 0. It's like that term is not even there. So you can cover that up. And then look at the rest of it. What does the rest of it say? 10y's got to be equal to 40,000. if x is equal to 0. So that lets you figure out, oh, y is just got to be, if I multiply 10 by 4,000, I'll get 40,000. So it quickly gives you a point on the line. Also, if you let y equal to 0, 10 times 0 is 0, so you might as well just cover that up and examine. When is 20x equal to 40,000? Oh, if x is 2,000. So you can pick off 2 points that have to be on this line and quickly graph it. So the associated boundary lines I have here is purple one, and this orange line here is coming, this was the boundary region of the constraints on weight. 6x plus 8y equal to 30,000 is the boundary region of that second half plane, second constraint about volume. Did the same trick, plugged in 0, used a calculator. 30,000 divided by 8 was 3,750. And when I let y equal to 0, 6x equal to 30, oh, that's 5,000. So I can quickly graph the purple line for weight, the boundary of the weight constraint, and the orange line, which is the boundary of the volume constraint. Now these boundary lines were of inequalities that 20x plus 10y has to be less than or equal to 40,000. If you look over here at this purple line, everything that's below that line, but within quadrant 1, would be considered something that matches the constraint on weight. So anything below that purple line or on it is feasible, it's doable, okay? Whereas the constraint on volume is symbolized by this orange line, that's its boundary, excuse me, and since the constraint is that volume has to be less than or equal to 30,000 pounds, then we have that 6x plus 8y has to be less than or equal to 30,000. Well, that would be everything underneath that orange line. Okay? All right, so where do the orange and purple boundary lines cross? Well, that's where the system of those 2 equations are simultaneously solved, right? Where did you learn how to solve 2 equations simultaneously so quickly? Oh, in chapter 6, right? Chapter 6, you were trying to solve 2 equations simultaneously, 2 linear equations simultaneously. You learned in chapter 6 that those 2 linear equations have an associated augmented matrix, which you can feed into RREF, which does all the Gaussian elimination on it and produces a matrix that is row equivalent to it and therefore has the same solution set as this one. Okay, so if you take that augmented matrix and put it into a system of equations, you get 1x, it's got to be equal to 200, and 1y has to be equal to 3,600. Oh, so now we know the coordinates of that. Sorry. Now we know the coordinates of that point over there. La, la, la. There we go, back over here. Okay. So here we are here. Okay, so now we know where the orange and the purple lines meet are at a point 200, x is 200, y is 3,600. Okay. Now, that point there is a corner point, we say, of the region of feasible solutions. And so I've colored in green here all the viable packing plans, the doable ones, the feasible ones. For every linear programming problem, there is a feasible region. If you're talking 7.3, this feasible region is usually some polygon in the plane, okay, a solid polygon. So all these points in green here are possible ways to pack the plane that meet the constraints. Okay? So for example, this point right here, these tick marks are 1,000 each. So right there is a point right here, 1,000, 0. That is a feasible packing plan. 1,000, 0, 1K, comma 0. Let's see, X is equal to 1,000. That means you're just loading it with 1,000 flats of water and no medical kits. It's feasible. The plane can take off. Stuff fits in there and the plane can take off. Does that packing plan maximize the number of lives saved? Okay. So you're like, well, no. Clearly, I could have this point in here. What's that one? That's 1, 1. Let's see, 1K, 1K. That means 1,000 flats of water, 1,000 medical kits. That also can still take off, and certainly that will save more lives, right? All right. Well, so if you had a bunch of constraints in a very complicated looking region, how are you going to know which one's going to maximize the number of lives or maximize this linear function? Well, that's where mathematically, using some higher level mathematics, we can prove that some particular XY pair that maximizes the number of lives saved, right? The output from f of xy, that linear function. That solution, some x and y pair in here, x star, y star, that does the best job, mathematically, we can prove that it must be on the boundary of the region. So the region is all in green here. The boundary has these 4 corner points, which when you're setting a computer to solving these things, we call these points pivot points. Okay. Finding the solution, you often pivot around these corner points. So higher level analysis tells us that the solution's got to be somewhere here on the boundary. Okay, and the corner point theorem says you can find the solution most quickly by first starting with checking the corner points. Where do those boundaries intersect? Okay. So here is a corner point table. Make sure good, you guys can see that. Okay. So the corner point table. Let's take a look at that. Trying to make sure you guys see it without me blocking your view. Okay, you can see this whole thing and all this over here, right? Okay, bring this down a little bit. All right, so here's the corner point table. So you list the x and y coordinates of all the corner points, all right? So the 0, 3750 came from that point right there. 200, 3600 was that point we found using our REF, where the 2 lines were intersecting. 2000, 0, that was this over here, and 0, 0 is over here. Now you'll notice we're not throwing in all the points we found over here, only those that are corner points of the feasible region that satisfy all those inequalities. Okay, so you find their x and y values. Now is when we finally are going to look at that objective function, f of xy equal to 4x plus 12y. I want to calculate the value of f at these different points. A way of really quickly doing that is to just say, okay, I need to know what 4 times x is, I need to know what 12 times y is, and then I'll just add these 2 up. You can do it quickly by hand to give yourself f of xy. So the number of lives saved by the first packing plan, where we have 0 flats of water, all medical kits, 45,000 lives saved. If we back that down a little bit in terms of medical kits, but throw in 200 flats of water, we save 44,000 lives. If we just throw only water in there, no medical kits, you can put 2,000 flats of water, that'll save 8,000 lives. And of course, So that's this point here. And of course, that's a corner point, 0, 0. When you're trying to maximize something, 0, 0, hardly ever a candidate for being the best one. It just if you don't fill anything into the plane, you're not going to save anybody. So you look at this and you say, which packing plan maximizes the number of lives saved? And so mathematically you say, oh, okay, this one. There's its packing plan. The packing plan is to put no water in the plane, only medical kits. Okay, now imagine this. You're flying to a region that has no fresh water. People have been out of water for days. You show up with this huge cargo plane and there's no fresh water. Mathematically, the answer to the question is this is the best packing plan. How can we get mathematically, the solution represents something that I think most people would agree with. If you're going to this region where people have been without fresh water for days, you'd better show up with some fresh water supply on there. First of all, how good are the medical kits if you're not giving water to the people who are operating them, who are helping people? You need to send water. So, next video, for the second go round, we'll come back and we'll add some more constraints to this. We'll come in here and say, you know what, y should be greater than equal to 0, but x, we should pump that up a little bit. How about we say that for x, you gotta have at least 100 flats of water in there, or there's nothing going to happen. So that's the next one.